All right, welcome to our podcast here on thermochemistry. Thermochemistry is a way for us to describe and discuss changes in heat energy in chemical systems. Let's just jump into this with a heating curve. Let's think about something familiar, ice. If I have some really cold ice, maybe it's been in the freezer, it's at -5 degrees Celsius, and we want to heat that up. At first, if we are adding heat, what will happen is the temperature will increase. So at this point, we're changing the kinetic energy of that substance. As we get to the freezing point, or the melting temperature, they're the same temperature, 0 degrees Celsius at standard, what we will see is that as the heat is continuing to add, and we start to have some of those particles melting, the temperature doesn't change anymore. So something fundamentally is different here as we go from just solid warming up to a phase change. During the phase change, we're changing the potential energy, and therefore we don't see a kinetic energy, a change in temperature like we do when we're changing the kinetic energy of heating just that single phase. Once everything is melted and we continue to add heat, now we're back to changing the kinetic energy, and up goes the temperature until we get up here to the boiling point. And at this point, we start to have the liquid turning into vapor, and once again, we don't see a temperature change. So we're just changing potential energy until we get everything into a vapor, and let's assume we have captured that vapor somehow. Now we can continue to heat the vapor and see another kinetic energy change, so the temperature will go up. There's got to be a way for us to quantify this, and in fact there is. Q equals mc delta T is the equation that we use for those instances where we have a temperature change of either the solid, the liquid, or the gas. So let's break down this formula. Q is energy, and energy is sometimes called heat, right, which can be kind of confusing because we do have delta T in this, which is a temperature change. If I say heat, I'm not really talking about temperature change. I'm talking about the energy involved. M is the mass of the material. C is the specific heat capacity, which we'll talk about in a second. And delta T, that's just the change in the temperature. So delta T, don't worry, if you ever get a negative value, that's possible. Let's say I had something that started at 100 degrees Celsius, right? That would be our initial, and it cooled down to 50 degrees Celsius. Guess what? 50 minus 100, that is negative 50 degrees Celsius. So we're going to have a negative delta T for anything that cools down. Let's just think about, for instance, that specific heat capacity, that C value. And if you've not heard specific heat capacity yet, you'll hear a lot about it. It's a physical property of matter. Water, for instance, has a specific heat capacity of 4.184 joules per gram degrees Celsius. Now what does that mean? It means it takes 4.184 joules of energy to change 1 gram of water by 1 degree Celsius. So if you're trying to heat it up, it takes an input of 4.184 joules for every gram to get it to raise by 1 degree Celsius. Let's think about sand, on the other hand. 0.80 joules per gram degree Celsius. It has a lower specific heat capacity. If you've ever been on the beach, you might be familiar with this. The sun has been blaring down, blazing, and it's heating up the sand. It's also heating up the water. But it's clearly not heating them up the same amount because you're going to tiptoe across that sand and your feet might be burning up, and you run yourself over to the water, put your toe in the water, and right, nice and cool. Well, how is it that that same sun has such a dramatically different effect on the temperature of the two? Well, look at the difference in the specific heat capacities. It only takes 0.8 joules of energy to get the sand, 1 gram of the sand, to increase by 1 degree Celsius. It takes many, many times more of that, like 5 times more energy to change that 1 gram of water by 1 degree Celsius. So not all materials are the same in their ability to change temperature when energy is imparted into them. That's specific heat capacity. Let's talk for a second about a chemistry convention I need you to be aware of. This, by the way, is not the kind of convention I was looking for. Here it is. If we have a negative value, I want you to think of negatives in this unit as energy leaving a system. And we can think about that back with our Q equals mc delta T. If we had something that cooled down, right, it cooled down, that would give us a negative delta T. C is always positive. We're not going to have a negative mass. That would give us a negative Q for something that has cooled down. It's cooled down, energy is left, it's exothermic. The opposite is true. If we have a positive delta T, it is heated up, Energy must have gone into it. It's endothermic. So keep that in mind. So let's look at a sample problem that you might encounter. Here we have silver. Specific heat capacity of silver is here. That's our C. How much energy? Energy is Q. Looks like we're solving for Q here. We want to raise this mass, 255 grams, by this amount of temperature. So we're going to have to use this to come up with our delta T. So let's just use Q equals MC delta T. We have 255 grams of silver. The specific heat capacity of silver is 0.230 joules per gram degrees Celsius. And the delta T, be careful with the delta T, right? Delta T is always the final minus the initial. So final, it's 961 minus the initial of 30 gives us 931 degrees Celsius, and it's positive 930 degrees Celsius, right? It heated up, so it's positive. Energy was put into that. So if we go ahead and calculate that now, we will come up with 54,600 joules, which is a really big number. And anytime we're getting up into the tens of thousands, it's probably a good idea to convert this into a more manageable unit. So let's turn this into 54.6 kilojoules. All right? Either one would be acceptable because I didn't ask you for joules or kilojoules, but 54.6 kilojoules is the better answer. Let's think about the other portion of our graph. All right? We just talked about where there was a changing temperature. Now let's talk about where the phase was changing. Here's what is our problem, right? Phase change happens here. Phase change happens here. Guess what our delta T is at phase change? Delta T is 0. So if we plugged in, it doesn't matter what numbers we plugged in there for the C or the M, we're going to calculate a 0 for the amount of energy it takes to change the phase of a material. And I think we can all reason that if I have a block of ice and I see that block of ice starting to melt, there must be energy going into that block of ice. So what we end up here with is a need for a different equation. Let's try this one. Q equals N delta H. What is N delta H? Well, Q is still energy, or heat. N is the same as N was in gases. N is moles. And delta H, we're going to talk about H in a second. It's technically this thing called enthalpy. But let's just say it is the heat needed for a phase change. And it's always given per mole of material, so it's the molar heat for a phase change. We're also dealing with potential energy changes here. I just want to remind you of that fact. This is your packet. It's a scanned part of the equation sheet in your packet. And I want to just draw your attention to a couple of things on here. First, it doesn't have this equation, Q equals N delta H. So you're welcome to put that in there, although I'm going to show you a way to solve these problems that doesn't require you to just kind of regurgitate stuff into that formula. But write it in there if you like. The other thing that I want you to see is that whenever we're talking about something freezing or melting, we are going to use this heat of fusion. So it's the delta got left off here for the molar heat of the phase change. So we have delta H of fusion, we have delta H of vaporization. So you may just want to write those in there too. So let's go back to our diagram here and try to match up the delta H of fusion and the delta H of vaporization with our phase change here. I think the vaporization one's fairly straightforward, right? Delta H vaporization goes with vaporization. What might not be so obvious is that the delta H of fusion is the term that we're using for melting. What also is kind of curious here, as you might be wondering, because you only saw delta H of fusion, delta H of vaporization. What do we do with condensation and freezing? Well, it turns out that freezing is just the opposite of melting. And the same amount of energy is involved. And if we think of our sign convention, if we have a positive delta H of fusion here, we're going to have pretty much the negative delta H of fusion being used for freezing. Now, sometimes you'll see this called the delta H of solidification. But just know that the delta H of solidification is equal to the negative of the delta H of fusion. Likewise, we have a delta H of condensation, which is equal to the negative of the delta H of vaporization. And if all of that just sounded like a bunch of mumbo-jumbo to you, let me just give you a number here, right? The delta H of fusion for water is 6.01 kilojoules per mole. All I'm saying is that if we are going to freeze some water instead of melt it, we are going to instead use the delta H of solidification, and that is negative 6.01 kilojoules per mole. So in your packet here, you are just given one of these, right? You're given the delta H of fusion. You can jot down here if you want that that is equal to the delta H of solidification is equal to the negative delta H of fusion. Right? So just change the sign, and now you can apply that number for the other kind of oppositional phase change. You could add in here, if you want, that the delta H of condensation is equal to the negative of the delta H of vaporization. So there you go. Let's see how we're going to calculate with this. We've got some ice that we want to freeze. Well, we want to make ice, so we have liquid water we want it to freeze. And we have 15 grams of it. Let me first show you just simply how you can plug this into Q equals N delta H. We know we want to find energy, so we're solving for Q. N is moles, so we're going to have to turn 15 grams into moles. And, you know, a little factor label here for every 18 grams of water, that's 1 mole. So that is how many? That is 0.833. Didn't really give myself enough room here, sorry. That's 0.833 moles. So we can put that here, 0.833 moles. And let's see, this is freezing. So this is going to be the delta H of solidification, which is the negative of the delta H of fusion. So this is going to be negative 6.01 kilojoules per mole. And notice how moles nicely cancels out, yields a kilojoule value. And we plug this into our calculator, we will see that we have a negative 5.01 kilojoules. All right? For those of you factor labelers out there, I would challenge you not to use this. Because look at our wonderful value here for the delta H of solidification. It is a conversion factor just waiting to be used. For every 1 mole, it's a 6.01 kilojoule loss of energy. So what we can do here is we can just start with our 15 grams, right, 15.0 grams, and for every 18 grams, that's 1 mole, and for every 1 mole, it's negative 6.01 kilojoules, and we end up with exactly the same thing. So you can factor label that, you can throw it into the equation, both answers will come out the same. Just watch your sig figs and have fun. All right. Here we've been talking about Q, right, energy. A lot of times we're going to be thinking in terms of what's called enthalpy. Enthalpy is what we will talk about when we're dealing with chemical reactions. Enthalpy is just how much heat energy is in a sample of matter, in a system. And it's also at constant pressure just by definition here. I want you to think about a chemical reaction. Right? In a chemical reaction, we have atoms that are in other bonding arrangements, so atoms and molecules, that they're going to break those old bonds, and then new bonds are going to form. Well, any bond that gets broken takes an input of energy. So in a chemical reaction, there's an input of energy that's required to get things going. And there's also going to be a release of energy whenever the new bonds are formed. That new bond is going to be more stable, and it will give off energy so that it stays in that bond. So here's the thing. We have an endothermic part of our reaction. We have an exothermic part of the reaction. So what's going to happen overall with the reaction? Is there going to be energy given off, like in a combustion reaction? Or is there going to be energy that is input in some kind of endothermic process, like if you break open one of those chemical cold packs? You know it gets cold, it's actually taking energy in for the reaction to occur, and that energy being taken from you causes you to feel cold. So overall, these are kind of competing. The energy that is breaking bonds and the energy that is given off when bonds are formed. If more energy is needed to break bonds than is given off, it'll be endothermic. If more energy is given off than is needed to break old bonds, it'll be exothermic. So let's look at this graphically. Okay, enthalpy is a way for us to kind of quantify the amount of energy in our starting amounts of material, our reactants, and the amount of energy that's in our products. And the difference between the starting point and the ending point is our delta H. Right? Typically, when we're talking about enthalpy, we're not just talking about H. We're talking about the change in energy. So from here on out, you're going to see H as delta H, the change in the enthalpy of the reactants and the products. So the way that we calculate this is we look at what is the energy of the products, or the heat content of the products. We subtract from that the heat content of the reactants. And let's look at this particular scenario here. Our products have less, so just use a little bar graph here. They have less energy than our reactants. So we're subtracting a big number from a small number, which will give us a negative delta H of reaction. And hopefully you can see here that this is exothermic. In order for the products to be lower in energy, heat must have been released during the course of this reaction. The law of conservation of energy says we can't just have energy showing up out of nowhere. We can't have it disappear into nowhere. What occurs here is the reaction system will give off that heat to the environment or the surroundings, so it'll feel warm. Negative delta H, once again that negative sign meaning exiting energy, energy being released. That's exothermic. What we're going to do is we're going to ask you to write thermochemical equations, which look a lot like regular chemical equations, except now you're going to include some energy information. So let's look here at the formation of water from elemental hydrogen gas and elemental oxygen gas. And don't get freaked out by this half coefficient. That is necessary so that this equation gives us 1 mole of product. Because what we're dealing with here are heats of formation. And this is the amount of energy given off to form 1 mole of something. So the half coefficient is a requirement there. But this is, by the way, one way that we can write a thermochemical equation. If we have an exothermic process, essentially heat is a product of the reaction. So we can write that amount of energy as a product on the right-hand side. That's one way we can handle this. The other way we can handle is we can just write our reaction equation as we would normally, and over off to the side, slightly separated from the equation itself, we would write delta H equals negative whatever the energy is. Here's what I need you to be careful with. When this is off by itself, the sign can either be positive or negative. Right? When it's exothermic, it's negative. Notice that we don't include this in the equation as a negative value. By putting it on the right-hand side, the product side, we are telling somebody who's reading this equation that it's exothermic by virtue of it being a product. Contrast what you've just seen with this graph. This graph here shows that our reactants start low in energy compared to our products. So our products have high energy. Our reactants have low energy. Big minus small is going to give us a positive delta H. This is endothermic. And you can kind of think about this as if it's a hill, right? It's a potential energy hill. You're going to have to push those reactants up that hill to get to turn into the products. There's an input of energy that's needed. This is endothermic. Positive sign convention, endothermic. Let's look at a thermochemical equation then for an endothermic process. Since energy is needed to get the reaction going, it sits over here on the reactant side. Right? And notice I've just kind of flipped this equation around from the last time you saw one. The formation of water from its elements is exothermic, but we can drive this reaction in the opposite direction. We can take liquid water and perhaps run an electrical current through it, and it'll take 285.8 kilojoules of energy to convert 1 mole of liquid water into gaseous hydrogen and oxygen. All right? We know it's endothermic based on our experience, or perhaps you've not thought about it, but here you go. If you're sitting there staring at a glass of water that you're about to drink, how often do you worry that it's going to spontaneously break down into hydrogen gas and oxygen gas, which, if ignited, will blow up in your face? Hopefully you don't worry about that very often. It's not going to happen without a sufficient and significant input of energy, because that decomposition is endothermic. And this is how we would write it as a thermochemical equation. The other way that we could write this is we could take that delta H and put it off to the side, slightly separated from the reaction equation. But keep in mind here we have to be careful with the sign. Make sure that I would like you to explicitly write a positive sign there so that I know that you know it's endothermic. If it's exothermic, I need that negative sign there. So write that positive in, and we'll know that this is an endothermic process, or write it over here as one of the reactants within the thermochemical equation, and we will know as well.